Hello and welcome back to another deep dive. Today we're opening up Unit 2, Electrochemistry.
It's good to be here.
But, we're not talking about the happy side of it. Usually when we study this unit in Class 12, we're thinking about batteries, cells, creating power. But today
We're looking at the dark side.
the destructive side, exactly.
It's what happens when nature decides to take that energy back. It's a process I think every student knows by name, but very few actually understand the chemistry of.
I agree. And before we even say the topic, I want to start with a little puzzle. I want you to imagine a simple experiment. You've probably done this in your school lab.
Okay, I'm listening.
Imagine we have 3 iron nails, just standard shining gray nails.
Right, got it.
Scenario 1, we put the first nail in a dish with completely dry air. Maybe we put some silica gel in there.
Okay, totally dry.
Scenario 2, we put the second nail in a glass of plain tap water. And scenario 3, we put the last nail in a glass of salt water.
Ah, okay. The classic setup.
Now, if we leave them for, let's say, a week, which one gets destroyed first?
Okay, let me think about this. The dry air one? Well, nothing's going to happen there. You need moisture.
Yeah.
That nail stays shiny.
Right.
The plain water one, you've got moisture, so there'll definitely be some rust. But the salt water one, that's the really dangerous one.
That's the one.
Yeah, if I had to bet, I'd say the nail in the salt water is going to be a total mess.
You would win that bet. It just turns into this mess of orange and red flakes really fast. And that mess, that destruction, is our topic today. We are diving deep into corrosion.
Corrosion, yes. A very critical part of the electrochemistry unit in the syllabus.
But honestly, why should we care so much? I mean, apart from it being in the board exams, is it just about rusty gates and old bicycles?
I wish it was just about bicycles.
Uh-huh.
I mean, if we zoom out from the lab for a second, corrosion is actually a massive global problem. We're talking billions of dollars lost every single year.
Billions. That seems like a huge number for just rust.
No, it's not an exaggeration. Think about all the infrastructure around us. Bridges, cars, huge ships, underground pipelines.
Right. Things we depend on every day.
Exactly. And corrosion isn't just an aesthetic issue. It doesn't just make things look ugly. It is a structural disaster.
Structural disaster. You mean things can actually fall down?
Absolutely.
Yeah.
Corrosion literally eats away the strength of the metal until the structure collapses. It's the main reason we have to constantly repair our highways and bridges.
Wow.
Honestly, if we didn't understand corrosion, modern life would basically fall apart.
Wow. That puts a lot of weight on this topic. It's not just a chapter in the book. It's keeping our bridges standing.
It really is.
So let's get into the core idea. If I'm a student who's struggling with this and I need the zero-level explanation, what is corrosion, actually?
At the simplest level, if you strip away all the complex terms for a moment, corrosion is essentially uncontrolled electrochemical oxidation.
Okay, uncontrolled electrochemical oxidation. That still sounds a bit heavy. Let's unpack that.
Okay, think of it this way. I like to call it nature's recycling.
Nature's recycling. That sounds almost positive, but corrosion is so destructive.
It's destructive to us, but for nature, it's just returning things to normal. Think about how we get metal in the first place. We mine ore from the ground, right? Like iron ore.
Right, it looks like red rock or dirt. Definitely doesn't look like a shiny nail.
Exactly. That ore is the metal in its natural, stable, oxidized state. It's sitting there for millions of years, quite happy.
Yeah.
Then what do? We take that ore to a factory.
We put it in a huge blast furnace.
Yes. We pump massive amounts of energy into it, heat, electricity, chemicals. We force it to give up its oxygen. We force it to become shiny, solid metal.
So we're forcing it into a high-energy, unstable state.
Precisely. The shiny metal we use is actually unnatural in a way. It's stressed. It's holding on to all that potential energy. It's like a stretched rubber band.
Waiting to snap back.
Yes. And corrosion is simply the metal wanting to return to its natural, stable state. It's snapping back, it's giving that energy back and turning back into ore.
That completely changes how I see rust. So rust is just the metal trying to become rock again.
That's a great way to put it.
It's almost poetic, like the metal is tired of being a bridge and wants to go back to sleep.
I like that. Let's do a quick visualization. I want you, the listener, to close your eyes for a moment. Imagine those huge blast furnaces. The fire, the roaring heat, all that energy being pumped into the ore.
Okay.
Now imagine nature slowly, quietly taking that energy back. The strong, shiny metal starts to crumble. It turns into reddish dust. That dust is the metal releasing its energy, returning home.
That really helps visualize the why, but for the exams, we really need to know the how, what's actually happening to the atoms.
Right. This is where we have to look at the surface of the metal under a microscope. It's a redox process. So two things are happening at the same time.
Oxidation and reduction, the classic duo.
Correct. So let's look at the first part, at a specific spot on the metal surface that we call the anode. This is where the destruction begins.
What happens there?
An iron atom, Fe, which is part of the solid metal, suddenly just lets go. It loses 2 electrons.
And when it loses electrons?
It can no longer stay part of the solid metal. It becomes an ion, A2+, and just dissolves into any moisture that's on the surface.
So it literally physically detaches and floats away.
Yes. The equation is Fe solid becomes Fe 2 plus ions plus 2 electrons. This is why you get pitting. The metal is physically disappearing from that spot.
That's scary. The metal is melting away atom by atom. But where do those electrons go?
This is a very common point of confusion. The electrons do not go into the water.
They don't?
No, they travel through the metal itself.
Oh, so the piece of metal acts like its own wire.
Exactly. The metal is the conductor. The electrons flow from that anode spot to another spot on the surface, which we call the cathode.
And what's waiting for them at the cathode?
The attackers. Oxygen from the air is waiting there. But oxygen can't just take the electrons by itself. It needs help from water.
This is where the moisture comes in.
Yes. At the cathode, oxygen takes those electrons, reacts with H+ ions from the water, and gets reduced to form more water.
So let me get this straight. At one spot, the metal dissolves. The electrons then run through the metal to another spot, where oxygen, with the help of water, eats them up.
That is the complete circuit. It's a tiny, self-destructing battery.
So if there's no oxygen...
the reaction stops. No electron acceptor, no circuit.
And no water.
No water. The ions can't move. The circuit is broken. The reaction stops.
So that gives us our perfect anchor definition for the exams. If you're writing this down, this is it. Corrosion is the unwanted, spontaneous oxidation of a metal in the presence of moisture and oxygen.
That's the one. And, I have to flag a really serious misunderstanding here.
What's that?
A lot of students think corrosion is just surface damage, like a skin rash. You just scrape off the rust and the metal underneath is fine.
It does look like that sometimes, doesn't it? Just a rough layer on top. Why is that wrong?
It's dangerous thinking because corrosion eats deep into the metal. The metal atoms are literally leaking. They're turning into oxide, which is brittle and has no strength. It's like turning bone into chalk.
Turning bone into chalk? That's a terrifying image for a bridge.
It leads to total structural failure from the inside out. A beam might look just a bit rusty on the outside, but inside, the metal connection is gone.
Okay, to help this stick, let's use an analogy. We mentioned nature's recycling, but is there another way to think about it?
I like to compare corrosion to a disease in a living organism.
A disease, like a virus.
Exactly. A healthy metal structure is like a healthy body. Corrosion is like a virus that needs certain conditions, moisture and oxygen to attack.
And once it starts?
It spreads. It starts at one spot, the anode, and it weakens the whole organism. And just like with a real disease, prevention is so much easier than the cure.
That's true. You can't really heal rusted metal. You can't turn rust back into steel.
You just have to cut it out and replace it.
That makes perfect sense. So can you tell us why we study this in electrochemistry specifically? Why not somewhere else?
That's a great question. We study it here because it solves the mystery.
Huh.
Why do refined metals fail? Without understanding the electrochemistry, the electron flow, the anode, the cathode, we just can't explain it.
So it connects the theory to real-world failures.
Yes. Humans have fought corrosion since the Iron Age, but we were just guessing. Now we use electrochemistry to fight back because we can understand and control the electron flow.
Okay, let's build a mental movie for everyone listening. Let's make this real.
Let's go to the ocean. I want you to visualize the steel dock. You have these massive steel pilings driven deep into the seawater.
Okay, I can see it. Big, dark steel pillars, smell of salt in the air.
Now look right at the waterline, the area where the waves are splashing against the steel. We call this the splash zone.
The splash zone sounds fun, but I'm guessing it's not good for the metal.
It's the disaster zone. Look closely at the metal there. It's a mess. This is where corrosion is the absolute worst. You see thick orange and brown flakes of rust just peeling off.
Why is it worse there? Why not say deep underwater where it's always wet?
Because in the splash zone, you have the perfect storm. You have plenty of water from the waves, but you also have plenty of oxygen from the air. Wet, dry, maximum oxygen, maximum moisture.
Ah, And what about deep underwater, at the bottom of the piling?
Surprisingly, the corrosion is much, much slower down there.
Really? But it's completely soaked in water.
Yes, but remember the cathode reaction. What does it need?
It needs oxygen to catch the electrons.
In deep underwater, there's very little dissolved oxygen compared to the air. So the reaction slows right down. The electrons have nowhere to go.
That's fascinating. The air part is just as important as the water part.
It's critical.
Yeah.
Now, in our mental movie, look closely at the steel. You might see some gray blocks bolted onto it.
Yeah, like little patches. What are those?
Those are blocks of zinc. And if you look, the steel around them is fine. But the zinc blocks are crumbling away. They're disappearing.
The zinc is dying.
It is sacrificing itself. This is the sacrificial anode. The zinc is corroding instead of the steel.
We have to unpack that in a minute. That's a brilliant trick. But last thing, zoom in on the rust itself, the orange flakes.
Yes, the hydrated iron oxide. Notice its texture. It's porous. It's brittle. It acts like a sponge.
So sponge, how?
It holds moisture right up against the metal. So once you have a little bit of rust, it keeps the area wet, inviting even more corrosion. It's a vicious cycle.
What a clear picture. The splash zone is the danger area, deep water is safer, and the rust makes everything worse.
Keep that image in your mind.
Okay, let's go back to our nail experiment. We said the nail in salt water corrodes fastest. Why salt, specifically?
It's all about conductivity. Remember, this is an electrochemical cell. We need ions to move in the solution to complete the circuit.
And salt water is full of ions? Sodium and chloride ions?
Exactly. It's an excellent electrolyte. It basically reduces the resistance of the water.
So it's like opening up a highway for the ions to move.
A perfect analogy. In plain water, it's a slow dirt road. In salt water, it's an expressway. Everything happens much faster.
That explains why cars in coastal cities rust so much faster. The salty air?
Precisely. Now, what about a nail coated in oil?
Right. If we tried that, what would happen?
Zero rust. Nothing.
Why not?
Simple. The oil creates a physical barrier. It blocks the attacker's oxygen and moisture from ever touching the metal. No contact, no reaction.
Simple, but very effective. Okay, let's go back to those zinc blocks on the dock.
Yeah.
The sacrificial anode. How does that technology actually work?
So this is sacrificial anode protection. It's not a physical shield. It's much cleverer. It uses the reactivity series.
Okay.
Zinc is more reactive than steel, which is mostly iron. It wants to lose its electrons more than iron does.
So it's more eager to oxidize.
Correct. So when you connect them, the zinc effectively says, don't worry, iron, I'll be the anode. It forces itself to oxidize and corrode, pushing its electrons onto the iron.
Which makes the iron the cathode.
Yes, and corrosion, the metal loss, only happens at the anode. So the zinc gets destroyed, but the iron, the ship's hull, stays completely safe.
That is amazing. The zinc literally sacrifices its life to save the ship.
It's brilliant engineering. You just bolt on a new piece of zinc every few years.
Okay, here's a tricky one. A counterintuitive example I've always wondered about. Aluminum is highly reactive, right?
Very reactive, much more than iron.
So logically, shouldn't an aluminum soda can corrode way faster than an iron nail? But it stays shiny for years. Why?
This is the classic, but actually, moment in chemistry. It confuses so many students.
What's going on there?
You're right, aluminum is more reactive. It should corrode instantly. And here's the surprise. It does.
It does, but I don't see it.
The moment pure aluminum touches air, it reacts. But the oxide it forms, aluminum oxide, is special. It forms a thin, invisible, rock-hard layer that perfectly seals the metal underneath.
So it forms a protective skin on itself.
A perfect, tight, non-porous skin. Unlike iron rust, which is flaky like a sponge, aluminum oxide is a shield. It stops any more oxygen from getting to the metal.
So aluminum protects itself with its own corrosion product.
Yes, and we call this passivation. It creates a passive layer. Iron creates a destructive, active layer. That is the key difference.
That is a huge distinction. Passivation. That's why we use it for airplanes and window frames.
Exactly. It paints itself with a protective oxide layer.
Okay, this has been so clear. But let's get ready for the exams. We need to lock in the marks. Let's go through the exam-safe clarity lines.
Let's do it. Rule number 1. Corrosion is spontaneous.
Meaning nature drives it. We don't apply power. Gibbs free energy is negative.
Correct. Rule number 2. At the anode, metal is oxidized. The general equation is M goes to Mn plus N electrons.
And remember, this is where the metal disappears. This is where the pitting happens, the anode.
Rule 3. At the cathode, oxygen is reduced.
So no oxygen, no corrosion. Simple as that.
Rule number 4. Salt water acts as an electrolyte.
It speeds up the process, it makes the kinetics faster, but it doesn't change the fundamental reaction. That's an important detail.
Very important. And finally, rule number 5, passivation protects.
Right. Don't confuse reactivity with the corrosion rate. Aluminum is very reactive, but it corrodes slowly because of that protective layer.
If you can remember those 5 rules, you'll handle any question on this topic.
Fantastic. Okay, let's wrap this up. A short summary of our whole journey today.
Let's do it. First, the core idea. Corrosion is nature's recycling. It's just metals wanting to go back to their stable, low-energy oxide forms.
Right, and the analogy, think of it like a disease attacking the metal.
Third, the mental image. Remember that steel dock? The splash zone is where it rusts the most, and those little zinc blocks are sacrificing themselves to save the steel.
And fourth, the key example. Aluminum doesn't rust away like iron because it creates its own perfect protective shield. That word is passivation.
And the final exam tip. The one thing to remember above all else.
What is it?
Remember the 3 requirements: metal, moisture, and oxygen. You remove any one of them, and you stop the process.
Metal, moisture, oxygen. The unholy trinity of rust.
Indeed.
As we sign off, I just want to leave you with one final thought. Think about that sacrificial anode again. We bolt a piece of metal to a ship, and its only job is to be destroyed so that the bigger structure can live.
It's a beautiful application of electrochemistry. By understanding how electrons flow, we can choose what gets destroyed. We can control nature.
Exactly. So the next time you see a rusty gate or an old car, don't just see damage. See the chemistry. See the electrons flowing, the oxygen attacking, and nature trying to take its energy back.
Electrochemistry is happening all around us every second.
Thanks for diving in with us. Good luck with your studies, and we will see you in the next deep dive.
Goodbye, everyone.